We're going to do section 5.1, estimating with finite sums. Let's look at example 1. It's summer vacation, and Mr. and Mrs. Gesterlin are driving from Northern California to Southern California along I-40. Since the speed limit is 75 miles per hour and there's not another car in sight, they set the cruise control at 75 miles per hour and cruise for 4 hours. How long did they travel in 4 hours? So how far did they travel in 4 hours? It would be 4 times 75, which equals 300. To visualize this graphically, I have a graph here. This is time, 4 hours, and 75 miles per hour. I'm at that constant speed for all 4 hours. My 300 would be the area under the curve. Would be this entire area with this rectangle. So 300 miles. Let's look at example 2. Find the distance traveled when velocity varies. A particle starts at x equals 0 and moves along the x-axis with velocity v of t equals x squared for time t greater than or equal to 0. Where is the particle at t equals 3? Well, since we don't have something that's linear, we'll have to approximate the area under the curve. And how we can approximate this area is if we use rectangles. So I could use rectangles. That would look like this. And notice, and if I use these rectangles, I'd have an over approximation. And other times you can have an under approximation. So in our next example, we are actually going to find the sum using different rectangles. So example 3. LRM, MRM, and RRM. What these stand for are the left, midpoint, and right rectangular approximation method. So the left rectangular approximation method, the midpoint rectangular approximation method, and the right rectangular approximation method. So we're going to use those 3 methods to approximate the area under the graph of y equals x squared from x equals 0 to x equals 3. We're going to use 6 subintervals. And this is going to be from A to B. When we use 6 subintervals, that gives us 6 rectangles with an equal width. So it would be 3 minus 0 divided by 6, which equals 1/2. This here is our left rectangular approximation method. This is our midpoint rectangular approximation method, and our right rectangular approximation method. This is an under approximation. This will be over, and our midpoint will be somewhere in the middle. To go about doing this, we first need to find our intervals. And since each rectangle is going to have a width of 1/2, that's how we do our intervals. So our first interval is going to start at 0 and go to 0.5. Our second interval is from 0.5 to 1. Our third interval is from 1 to 1.5. Our fourth interval is from 1.5 to 2. Our fifth interval is from 2 to 2.5. And our final interval is from 2.5 to 3. Next, we're going to find the midpoints of each of these intervals. So you take the 2 endpoints and divide by 2. So our midpoints would be 0.25, 0.75, 1.25, 1.75, 2.25, and 2.75. Let's go ahead and use our left rectangular approximation method. So when we do this, we take the width of each rectangle, so 0.5, times f of each left endpoint. So f of 0 plus f of 0.5, our left endpoints, plus f of 1 plus f of 1.5 plus f of 2 plus f of 2.5. And I got our left endpoints from the intervals up here, 0, 0.5, 1, 1.52, and 2.5. This would be 0.5 times f of 0. So 0 squared is just 0. Plus f of 0.5. 0.5 squared is just 0.25. F of 1 would be 1 because 1 squared is 1. F of 1.5 squared, so f of 1.5 or 1.5 squared would be 2.25. Plus f of 2, which would be 4, plus f of 2.5, which would be 6.25. This would be, in total, 6.875. So this is your width times your length. Your right rectangular approximation, it's the width of your rectangles multiplied by our right side of our intervals, f of that. So f of 0.5 plus f of 1 plus f of 1.5 plus f of 2 plus f of 2.5 plus f of 3. This would be 0.5 times 0.25 plus 1 plus 2.25 plus 4 plus 6.25 plus 9. And this would equal 11.375. And then our midpoint rectangular approximation method would be 0.5 times f of 0.25 plus f of 0.75 plus f of 1.25 plus f of 1.75 plus f of 2.25 plus f of 2.75. This would then equal 0.5 times 0.0625 plus 0.5625 plus 1.5625 plus 3.0625 plus 5.0625 plus 7.5625, which would be about 8.9375. So as you can see, using either the left endpoint, the right endpoint, or the midpoint, you can come up with different approximations for the area underneath the curve. So how far the particle traveled in total distance. So let's go ahead and look at this example here. A test plane flies in a straight line with positive velocity v of t in miles per minute at time t minutes, where v is differentiable of t. Selected values v of t for 0 to 40 are shown in the table below. Use a midpoint Riemann sum with 4 subintervals of equal length and values from the table to approximate the velocity from 0 to 40. Show the computations that lead to your answer. Using correct units, explain the meaning of the integral from 0 to 40 of v of t dt in terms of the plane's flight. So we need to use 4 subintervals. So this would be interval 1. This would be interval 2. This would be interval 3. And this would be interval 4. We want to use the midpoints. So the midpoint of the interval from 0 to 10 would be 5. The midpoint of the interval from 10 to 20 would be 15. The midpoint of the interval from 20 to 30 would be 25. And the midpoint of the interval from 30 to 40 would be 35. So first, we get our intervals. So my intervals are 0 to 10, 10 to 20, 20 to 30, and 30 to 40. 4 subintervals of equal length. If I want to use my midpoint rectangular approximation method, these intervals have equal length of 10, and I would use the midpoint of each of them, so it would be 9.2 plus 7.0 plus 2.4 plus 4.3. This, when I put it in my calculator, would be 229 miles. So the test plane flies approximately 229 miles in 40 minutes.